Welcome everyone to the session. My name is Misha Brukman. I'm the product manager for Google Cloud Bigtable. And with us today, we have Stein from eBay, who will talk about how eBay brings together billions of product listings to enable new shopping experiences using Google Cloud Bigtable. Leon?
Hi. So first, a few facts about eBay. eBay is a truly global company. We have 167 million buyers in over 200 countries all over the world. Over 57% of our business is international. And we are pretty big on mobile, right? With close to half of business coming from mobile and 348 million mobile app downloads. Other brands of eBay include eBay Classifieds and StubHub. So at the heart of what eBay does is eBay catalog. And eBay catalog is pretty big, and it's very rich and very complex. So we have well over 1 billion listings available worldwide in eBay catalog at any given moment, and over 15 million listings are added to the catalog every day. And catalog is comprised of many different data sets coming from many different data sources. So if you look at an eBay listing, you will see obvious things like title, price, variants, description, attributes, images, right? But there are also many data elements that are not visible, and they are computed behind the scenes by many different algorithms to enhance selling and buying experience. So it's not unusual for an eBay listing to take megabytes, not counting images. And of course, the volume of updates of eBay catalog is, of various data sets in eBay catalog is very high, and we'll talk more about that. So with our team, which is new product development team, and we build applications on Google Cloud Platform, first thing we wanted to bring over is the catalog. And we needed a scalable platform, right, to effectively enable new shopping experiences globally, right, showcasing eBay inventory. We wanted a platform that allows us to scale on demand with data volume and traffic. We wanted to be able to iterate quickly and integrate with data-heavy AI technologies. Our first application that we launched this last October is eBay ShopBot. So you can go, if you happen to have a mobile device or laptop, you can go to ShopBot, ebay.com, and start playing with it. So eBay ShopBot is a newer, smarter, and easier way to shop in chatbot context, right? And it leverages AI with NLU, dialog management, and also visual search. So you can snap a picture of an item you're interested in and submit it to ShopBot, and it will hopefully find something very close. So there were a number of challenges, of course, with bringing all the data over to Google Cloud Platform. First, the catalog had to be brought from many different sources. And we wanted to bring it in a way that is really convenient to work with, so that instead of having different pieces of catalog in different systems, we wanted to have all data effectively together, so it's much easier to work with it in different contexts and enable different shopping use cases with it. So we also needed to provide a highly scalable and consistently fast way of accessing catalog data. right? We have hundreds of thousands of updates per second on catalog data, right, with hundreds of megabytes written, and very high volume reads. For example, an update to a catalog results in search index update, and in order to re-index a listing in real time, you need to know more information about the listing than happened with just that update. So we have more reads in terms of volumes than writes. So our reads are in many gigabytes per second. And of course, we wanted very low latency replicating catalog data from eBay core system to Google Cloud Platform, so that it is important in retail domain to have up-to-date data. So if listing is no longer available, we don't want to show it. If price changes, we want to show updated price. And we also needed very high consistency of the data, so that in case if an update is missed in near real time, we still want to make sure that we have a mechanism that repairs this data, so the data, replicated data, is eventually correct and consistent with what we have in core, right? So, for example, if price changes and or listing got bought and we didn't catch this event, we want to have a mechanism in place that ensures that we will have data eventually correct in Google Platform. So, about Google Cloud Platform. It is, there are many great features, and I just want to highlight a few of them that we really leverage. First, it is global presence, and eBay as a global company needs a platform that supports global presence really well. Also, comprehensive and highly coherent technology stack, and we are cutting edge. We like to work with newest technologies, and GCP provides those newest technologies, right, for us. And it has leading support for Kubernetes with containerization, and we leverage Kubernetes in many of our services. So it was very important to us. And finally, there are some unique offerings in GCP. There are many of them, but for this talk, I want to focus on Bigtable. That was the data storage that we've selected for the catalog. And we will go in more detail on how we use Bigtable. With that, OK, so this is a high-level diagram that just covers our data ingestion pipeline. It doesn't cover our whole infrastructure on GCP. It's much bigger, but this is just the part that is responsible for getting the catalog from eBay core systems to GCP. And in the next slides, we'll go in more detail in parts of it. And with that, I'll pass it back to Misha for a deeper dive in GCP and the systems.
Before we talk about Google Cloud Platform in more detail, I thought it would be worthwhile to look at the history of Google and where Google comes from and how we arrived to the point that we are today. Google originally set out to organize the world's information and make it universally accessible and useful. And for that, Google built web search. Now, that is a very specific application. There's a lot of very search-specific algorithms and details that go on behind the scenes. But even with this very specific application, Google had to solve a number of very generic, standard big data problems to be able to enable the search application service. For one, we had to be able to store a large amount of data, and depending on the type and the content of the data, we needed to use a different storage system for those different types of data. So we needed to use file systems, databases, and other types of storage systems. Once we had that data, we needed to be able to process it at scale. And we needed to both be able to process that data in batch mode to analyze the link structure of the World Wide Web, as well as to update data in real time as web pages change. So we needed a real-time streaming pipeline as well. And then to be able to serve the data, we needed to be able to deploy and update our services, and we use a microservice architecture. We needed to update them quickly and without any downtime. Google built a number of generic infrastructure components, and with that, it enabled a number of teams across many different domains within Google to build a number of services that each of which serve over 1 billion users. So each of the services that you see featured on the slide, from Google itself, google.com, to Google Play, Chrome, Android, YouTube, Maps, Gmail, and Google Cloud Platform, each of those serve over 1 billion users. And the way that we've been able to do that is by using similar architecture and infrastructure components across all of them. So all of these services benefit from the same hardware infrastructure, networking, the global network that we have built to enable them to operate at the scale that they do. Not only the hardware, but also the software. Over the years, Google has built a number of software components to enable all those projects to scale, starting with file systems such as GFS, onto processing systems such as MapReduce, Flume, and Millwheel, to analytic systems like Dremel, databases like Spanner and Bigtable, and container managers like Borg. Google has been able to build these generic systems such that each of those teams were able to innovate and build the domain-specific components that they needed for their services without having to reinvent and resolve the standard big data problems that they would all face consistently. And now, with all of these technologies that Google has built over the years to support all of its own products, we're making all of them available on Google Cloud Platform in the various areas of compute, storage, databases, big data processing, and machine learning, so that anyone can use these building blocks to build their own applications and their own services and have them seamlessly scale to serve millions and billions of users. Let's talk about a couple of these components in more depth. So for one, as I mentioned, we needed to be able to run systems, and we needed to upgrade these systems very quickly and efficiently with no downtime. Google started off by building container support by writing the C group support that we open sourced and contributed to Linux over a decade ago. But we also needed to be able to run these containerized workloads. So we built Borg, and then we open sourced a container manager called Kubernetes, and now we've created a managed service offering that uses Kubernetes, and this is Google Container Engine. Container Engine provides cluster management and orchestration for your containerized workloads. It also provides a private container registry for you to deploy your applications. The applications can use a declarative specification for resources that Kubernetes and Container Engine will enforce. And it also provides auto-scaling to meet the needs of growing applications. We also needed to have a file system that would scale to the growing needs of the internet. And so what we started off was, we built Google File System, and then we've upgraded that with Colossus. And today we offer that as a service as Google Cloud Storage. Google Cloud Storage is an exabyte-scale storage system. It provides high throughput, it provides replicated storage across regional and multi-regional modes. It also provides several different types of classes for your data, depending on whether your data is hot or cold or somewhere in between. And it uses the same API, so you don't have to change your code depending on which type of data that you're accessing. It also provides an HDFS-compatible connector for Hadoop, so you don't have to change your code if you're using Hadoop with HDFS. It will work seamlessly with Google Cloud Storage, again, across all those different storage classes and different bucket types. Once we have the data, we need to be able to process it at scale. And we're talking about both static and streaming data. Google's written several different systems from batch to streaming, such as MapReduce, Flume, and Millwheel. And then we combined all of those together to offer as a single product Google Cloud Dataflow. Then we went a step further, and we've open sourced the SDK behind Google Cloud Dataflow as Apache Beam. Apache Beam recently became a top-level project in the Apache Software Foundation. Dataflow combines both batch and streaming modes, so you don't have to change your code from one to the other. You can write your code once, and you can run the same code in both batch and streaming modes. Dataflow provides auto-scaling and dynamic task sharding so that you're not affected by long stragglers doubling or tripling the total length of your job. As Dataflow notices that some of the workers are struggling to process the data, it will dynamically split those data and then auto-scale and provide more workers to handle those shards that are taking longer than others. Dataflow provides connectors to our various storage systems such as BigQuery, Bigtable, and Cloud Storage, so you can read and write data from anywhere. And as I mentioned, code that uses the open source Apache Beam SDK also becomes portable. You can run Apache Beam workloads on Dataflow as well as Spark and Flink. We also wanted to be able to run open source processing engines such as Hadoop and Spark directly. So for that, we built Google Cloud Dataproc. Dataproc allows you to run Hadoop, Spark, Pig, Hive, and other open source big data systems. It also provides connectors to Bigtable, BigQuery, and Google Cloud Storage, so again, you can read and write from anywhere. And because it can read and write data from anywhere, you don't have to write in stateful clusters. Instead, you can run stateless clusters that have their storage external to them, which means you can very quickly and easily spin up clusters, run the jobs that you need, and spin them down. Dataproc also provides a higher-level jobs API, such that you can just submit jobs rather than thinking about clusters, long-running clusters, managing those clusters. We also needed to have a petabyte-scale database. When we used to build our search indexes in batch mode, in bulk, it took a long time to keep rebuilding the entire search index. It also made the index grow stale over time because we would not be able to catch the really quickly changing web pages as they changed in real time. So what we needed was a real-time, low-latency access to data sets scaled into the petabytes. And for that, we wrote Bigtable. And we're now offering Bigtable as Google Cloud Bigtable as a fully managed service on Google Cloud Platform. Bigtable is a fully managed NoSQL database. As I mentioned, it provides petabyte-scale data scale storage with low latency access for both reads and writes. It provides very seamless scalability for throughput, and it learns and adjusts to access patterns. Let's look into more detail about those last 2 points and how we provide that. So first, let's talk about the structure and the schema for Bigtable. Bigtable is a NoSQL, sparse, white column database. So what that means is that Bigtable has a single key, which is the row key. It does not do joins, and it only does single row transactions. It's sparse, so that means whenever you don't store the data in any one of the cells, it does not count against the storage. It is white column, which means that you can create column families, and within each column family, you can create essentially an unlimited number of columns. So you can store any number of data items keyed to a single row as you need. The way to think about Bigtable as a data model is as a three-dimensional spreadsheet. There are rows, there are columns, and each one of the cells has an arbitrary number of versions, which are keyed with a 64-bit integer. You can treat that 64-bit integer as time, and that is a very common use case, but you can also treat that as just an arbitrary version and just assign them versions as 1, 2, and 3. Bigtable is an unopinionated storage system, so you can store any type of data. It's uninterpreted, so they're just bytes. And there are many different applications that can be built on top of Bigtable. However, for each one of those, you would have to design custom row key schemas. For a number of standard use cases, there are open source systems that already predefine those schemas such that you can implement these common use cases very easily. So Bigtable has native support for time series because it has that third dimension of time, but you would still have to carefully design your time series schema to make sure that it performs well. Or you can use one of the open source systems, such as Heroic by Spotify, or OpenTSDB, which is an open source time series database. In fact, Spotify runs their monitoring system today on Bigtable using the Heroic system. Alternatively, if you need to run graph workloads, of course you can implement a graph schema using something like adjacency lists using the white column database. You can also use one of these two graph abstraction systems, such as HGraphDB or JanusGraph, to provide you with a standard Tinkerpop API implementation on top of Bigtable. JanusGraph is something that we just launched recently in cooperation with several other companies, IBM, Hortonworks, Xpero, and Grokken. This is a new project as of 2 months ago in the Linux Foundation that is now working with Bigtable. It also supports other open source white column databases. Let's talk about the Bigtable implementation and the architecture behind it. So this is a somewhat simplified architecture, and we're going to go into depth in the next few slides. Clients connect to a load balancing proxy endpoint, which then connect to the processing nodes of Bigtable server nodes. In the next few slides, I'm going to remove the load balancing proxy layer for clarity to show where the requests are actually routed. But just remember that there's a single endpoint, so there's no need for a discovery service for each client to know where to connect to. All the clients connect to a single endpoint. One interesting thing about Bigtable is that as a database, Bigtable itself is actually stateless. Bigtable does not store any data. And this is actually true for all the other big Google storage systems. Bigtable, Spanner, BigQuery, and Google Cloud Storage all use the Colossus file system. So Bigtable nodes provide you with access, and they mediate the requests between the clients and the data, but the Bigtable nodes themselves don't store any data. Now, this provides a couple of interesting features as to how Bigtable operates. Let's say we are looking at an access pattern such as the one in the diagram, where the Bigtable node on the left is getting more requests than the other nodes, and that is because it is managing the data in Colossus, the regions A, B, and C, and that data appears to be popular with the clients. As Bigtable noticed that one of the nodes is getting more activity than others, it can easily reassign the ownership of the data to a different node, and the requests will be rerouted automatically. Again, remember there's that load balancing proxy layer. This is possible to do quickly because we're not actually moving any of the data. None of the nodes actually store the data within their own containers. So this is just a metadata reassignment, which happens very quickly. We don't need to copy terabytes or petabytes of data to be able to do this reassignment, so this happens very quickly. In fact, this happens all the time. So for example, if you wanted to scale the cluster, the same thing happens. It's very easy and seamless to scale clusters because, again, we're only moving the reassignment. Now, remember that each node has to have exclusive access to the data that it's managing because we're providing atomic single row transactions. This means that you can easily scale the clusters up, but this also means that you can easily scale the clusters down. So if you know that you need to do some workloads that will change in the size and type and nature of the workload, you can easily send an API request, resize the cluster up, do your additional processing with Dataproc or Dataflow or any other system, and then scale it down. And Bigtable will handle the management automatically. One interesting thing that also happens is, with Bigtable, the throughput scales linearly in proportion to the number of nodes. For one, because it's very easy to scale the clusters, and because the nodes themselves don't talk to each other, they're completely independent, the throughput scales in proportion to the number of nodes. In many other storage systems, this performance would typically flatten out after a while. But with Bigtable, it scales linearly. So whether you have 3, 30, 300, or more nodes, the throughput and processing will scale linearly. Last year, we did a test with one of our customers with 3,500 Bigtable nodes and 232 core VMs. And again, the throughput there scales linearly. At this point, I'll pass it back to Leon to talk about the architecture that you saw earlier in more depth.
Thanks, Misha. So going back to our eBay use case and our challenges. So we had to synchronize the catalog over to Google Cloud Platform in near real time with low latency, I'm talking about single seconds of latency, and with high consistency. So we also want to serve the catalog data to other services that consume it on the Google Cloud Platform with high read volume and low latency, right? And we also want to support the vision use case, right? So we want to keep listing images in Google Cloud Platform for training vision models. And also, we want to keep AI vision signatures, which are pretty much feature vectors over images, somewhere so that we can extract and build image search index out of them. So we've selected Bigtable to store catalog data, which may sound unusual. It's not like Misha mentioned, Bigtable is unopinionated data store. So it worked really well for us. It is highly scalable and reliable solution. And with amount of data and volume of updates and reads, right, it was a store that could handle this. It has excellent performance. And another important consideration for us is the API, the Java API to Bigtable is actually based on HBase client. So if you don't know about HBase, Apache HBase is open source NoSQL database that was modeled after Google published Bigtable paper. So HBase was modeled after Bigtable, and the ideas kind of that Apache Bigtable utilizes are the ones that were introduced by Bigtable, and it's very nice that Google chose to implement Java client as fully compatible HBase client. So you can write code against Bigtable as you would write it against HBase. So compared to HBase and another very popular NoSQL database, Cassandra, the performance of Bigtable is significantly higher. So in addition, it is fully managed, of course, on Google Cloud Platform. So while Cassandra and HBase deployments are non-trivial to support, and especially at large scale, it is well integrated with GCP console and rest of the Google Cloud Platform stack. As Misha mentioned, there are connectors from Dataproc, Dataflow. And going back to performance, this chart shows a benchmark that actually Google made a couple of years ago comparing Bigtable performance to HBase and Cassandra. And you can see that the writes and reads is where Bigtable consistently takes 6 milliseconds per operation, and HBase and Cassandra are in hundreds of milliseconds. Well, Cassandra does better obviously on writes, because that's what it was optimized for. So another great features of Bigtables is seamless cluster resizing. So we run pretty large Bigtable instance on hundreds of nodes, but sometimes we need to make bulk loads that require much more resources, and and we can add hundreds or a few hundred nodes to our Bigtable instance, and in 20 minutes, it is all rebalanced and ready to go, and we can send the load to Bigtable, and then after we are done, we can remove these nodes, and it just continues going. We don't see any degradation in performance as rebalance is happening. It works really great. Also, the administrative operations against Bigtable, like adding new tables, changing column families, they're all non-blocking, and they can be done on running Bigtable instance. And again, there is no effect on running applications. Finally, a lot of magic, I guess, with as we been working with Bigtable for the last year, we realized that a lot of magic with performance goes into the client, and Google is actively working on open source Bigtable client, and we're very happy with all the optimizations that we've seen that went into the client over the past year, and we are sure it will continue going this way. So back to the diagram. So this is the diagram at high level. You can see that we use many different components on GCP platform just to support catalog ingestion. So let's focus on our near real-time synchronization pipeline. So in eBay core on the left, you see we have our private cloud, where we have compute, storage, and streaming, right? Where data is originally hosted. So we have exposed all the updates that go to different data sets that comprise eBay catalog. We have exposed them as Kafka streams. So there are dozens of different data sets that compose eBay listings, which are partitioned across many Kafka streams. So we are dealing with close to 500 individual streams. And these streams are consumed by storm topologies that we manage and run on eBay side. If we probably could have considered Apache Beam for that. But we have Storm topology that consumes these events. It aggregates them in micro batches, does deduplication, and then sends these micro batches over to GCP. We use Google Cloud Load Balancer, right, that fronts Kubernetes cluster of our catalog service that receives these micro batches. And micro batches may contain anywhere from 1 to a few hundred records, right? And then insert them into Bigtable. So now let's look at the table that where we store that data. So we chose to store the data in the original format that we get from core. And the reason for that is we want to be really flexible in how we expose this data. So the most flexibility for us would be not to make any changes to raw data, but rather have a separate table where we convert and transform the data. So having data in the original format in GCP gives us ability to go back and recompute our target model at any point of time. The data sets that we get from core are encoded in Apache Avro format. So every cell here actually contains a record with multiple fields that are encoded in Avro. We have a separate table where we store Avro schemas, so we don't lose track of those. And you can see that we have multiple column families. So in fact, for every data set, we have a separate column family, and that gives us, and that helps us as isolating the load on Bigtable, right? Because the nice thing about column families is that if you have independent reads, right? So if you read from or write to a particular column family, it doesn't feel other column families, right? So you can have many of them, you can have hundreds of column families, but you only, when you do writes or reads, only ones that you touch matter. So in every column family, we have two columns, one for metadata that captures information on where the record originated from, some correlation identifiers. Some of the streams that we consume come from Oracle Golden Gate, so it will capture Oracle row IDs, transaction commit sequences, and whatnot. And then the Avro record that contains the data itself. Right, so you will also notice that we have NRT, the column family is prefixed with NRT, which stands for near real time, and DW. So we'll cover it later. And for some data sets, these are duplicated. So the DW are coming from batch. And I'll explain later why we do that. Now, going to row key design, right? As I mentioned, listings are comprised on many different kinds of records, and you can look at it as hierarchical parent-child data structure. So if you have a listing 1 to 3, it may have variants, right, 1 and 2. So we prefix, right, the key by the listing ID. Then we put colon qualifier for the kind of child we are writing, and then colon, and then the identifier for that child. And then if you have grandchildren, we'll keep appending to the key. Now, so that allows us to keep all the records belonging to the same listing together, which is really important with Bigtable because they can be scanned together really efficiently. So Bigtable allows scanning by key prefix, and these records are physically stored together, so you can read them really quickly. Now, with key design, it is really important to avoid hotspotting, which is having keys that are monotonically increasing or decreasing. So with eBay listings, we do not have exactly that, but the distribution of keys of listing identifiers in eBay is not exactly uniform. So we chose to reverse lexicographically the listing IDs. And that makes the distribution uniform and avoids any potential interference with how the data is distributed in Bigtable and how it is scanned. And you will also notice that these gray cells contain no data, and which is fine because Bigtable doesn't punish you for having sparse data sets with, right? So you don't pay, you don't, right? When if data is not there, it doesn't take space. So as a NoSQL database, Bigtable supports retrieval by keys. So if you have a key, you can get the value, or you can scan a key range. These are basically two fundamental access partners with Bigtable. So you cannot have secondary indices supplied by Bigtable itself, but you can make one for yourself as another table in Bigtable. And we use that since we need to know. We've accumulated over a year or so that we've been running on Google Cloud Platform, we've accumulated billions of listings and hundreds of terabytes of data in Bigtable. However, it is really important for us to know which listings are available right now, which is about 1.1 billion. And we want to scan the listings that are available right now really quickly. For example, if you want to rebuild search index from scratch or to run some reporting. So for that, we maintain a separate table, which is really small or really narrow, that only contains the identifiers of the available listings. So if listing becomes unavailable, we just delete a record from Bigtable, or if we get a new listing that is available, we just add a record here. And the identifiers, the listing identifiers are prefixed here by site IDs. And site ID stands pretty much for market where listing where item was listed, United States, UK, and so on. This allows us to scan just for available listings in United States or just for available listings for UK, so we can rebuild the index just for the subset of markets that we want to. And then we have a few columns, in this case, we add seller ID and leave categories ID in case if you want to do additional filtering as we scan this data without having to do lookups against raw listings table. Now, the value of, so as I mentioned, the values that we want to bring to the stack of applications that use catalog is by representing eBay catalog in a coherent, convenient way to other applications. So we've developed a schema for or a data structure that represents eBay catalog, which is much more convenient than the raw data that we get. So we store the data in a separate table, and we chose protobuffers to represent the schema, that schema. And we also break it up into fragments that we store across column families so that we can retrieve them separately for efficiency. So in case if you only need to know about variants, you can just scan that column family, right? We also, we use here each record contains a single listing ID. Each record contains a single listing, so the keys are lexicographically reversed listing IDs. And we also have this source version column that we use for lazy rebuilding catalog model. So usually we rebuild catalog model as we ingest new data. But in some cases, when we do batch operation, we can just increment the version right, in this table without rebuilding the whole model. So next time we need to read, we know that the model that we have in this table is stale, and we need to rebuild it. So next, the catalog service. So catalog service is running, as I mentioned, on Kubernetes on container engine. And we've chosen to front all access to Bigtable, right, by this service, so that clients that need to deal with catalog data, they have to go through catalog service. They don't have to deal with intricacies of Bigtable storage. So, and this service, you can imagine, it runs on pretty large number of instances because it gets a lot of read and write hits from all over. And container engine really helps us with managing deployments and scaling of catalog service. We have it fully integrated in continuous delivery pipeline that we run on core, and we write our images to container registry in Google Cloud Platform, and do rollouts in managed way, so it doesn't impact the capacity of our service. So it's been working really, really well. So this service is processing many thousands of batches per second, right, with every batch containing hundreds of records. So it's pretty heavy volume service. Now, I've mentioned that we needed a mechanism to ensure that we don't miss updates, right? In case if our near real-time pipeline is designed not to miss updates. So if for some reason we cannot write to Bigtable, we'll just go into this infinite retry loop, and then and then alert, and then someone has to come in and fix the pipeline, right? So that updates keep flowing. But it happens that upstream we might miss an event just because something happened upstream from us. So for that, and also to support data sets that are not available in near real time, we've added a batch pipeline. So batch pipeline synchronizes some of the main data sets about eBay catalog that contain price and availability information. So and we do it daily. So in case if we missed price or availability update at the end of the day, we'll catch it with a batch update and reconcile it. And so this inconsistency will live in our catalog for up to a day. We also have a dashboard for highly visible items. We can compare what is in core systems to what is in Bigtable, and then force synchronization. Now, the way batch pipeline works, first we have, of course, batch data is extracted from our Hadoop and Teradata data warehouses that run in core, and then this extracts that we run daily are broken into many small fragments containing, up to a few million of records, and we load these batches over to Google Cloud Platform, and we put them in Google Cloud Storage. And after each fragment is transferred, we invoke a call to catalog service so that it can load it from Google Cloud Storage and stream it from Google Cloud Storage and stream this batch into Bigtable. This operation is that important. So if something breaks, we can repeat until we succeed. And we keep track of all the fragments, both on core in a simple SQL database, so we can account for each fragment. So we make sure that everything is loaded completely. And we also keep track of this batch operations on Bigtable side, so that our load operation is effectively non-blocking. So we just make a call to load, and then we pull against the HTTP API of catalog service to check whether the fragment is loaded, which may take from a few seconds to a couple of minutes. So next part is integration with search. So search is really the main consumer of catalog data for us. So it has to reindex listings in real time as listing information changes. In retail world, you have to index in real time. We've chosen to put pub/sub between our search index build and our catalog service just to give a little room for our index build process to adjust to spikes in the number of updates. So if there is a big spike, pub/sub will buffer it, and search can work at its own pace. Search indexing can work at its own pace. So the way it works, the way it works, as data is pushed to catalog service, the identifiers of the listings that are affected, along with some metadata that tells which data set this update is coming from, and a bitmap containing the indices of columns that got touched by that update, is put on pub/sub. So each message may contain a number of listings corresponding to the microbatch along with the metadata. So search index build consumes these messages from pub/sub topic, and based on what changed about listings, it decides what it needs to fetch from catalog service. It usually needs to fetch more than just the data sets that changed, because indexing involves pretty complex operations that requires knowing a lot about a listing. But in certain cases, it can just take, it just needs to know a subset of listing data, and really helps us with reducing the load against catalog service and Bigtable. So that is pretty much how our near real-time search indexing works. So next, as I mentioned, our ShopBot supports image search. You snap a picture, or use an existing picture, you give it to ShopBot, and it finds items that are available that look similarly. It works really well. It's the image search that we have. The image models are developed in-house. In fact, we've just submitted, a couple of weeks ago, a paper to KDD 2017, where we describe in detail how we build our image models and how our pipelines and image serving and image search works in detail. So if you're interested, please ping me offline. I can give you more information about that. So our catalog service and Bigtable will ultimately participate in the process of helping enable image search. So what happens is, as we get catalog data, we detect if images, if we have new images or list of images for a listing changed. So in response, we download these images from eBay core. We save the images in GCS, in Google Cloud Storage. And we also have a GPU cluster where we run our own vision models, where we pass the images to compute feature vectors, right, representing these images, and storing these feature vectors, which are, half a megabyte, 512 bytes, right, half a kilobyte records, right, to Bigtable. So here is how our images table looks like. So it has image unique identifier as a key, and it stores a couple of versions of image signatures. The reason we store a couple of versions, it helps us transitioning from one vision model to another. So in case, right, it helps with smooth transitioning of that. Finally, we have another small table that just keeps image hashes over the bits of images. And that helps us deduplicating the images. In our business, we find that quite a lot, about 20% of images are actually duplicates, and they're submitted under different names. So this helps us identify if an image, if we already have seen an image in the past. In that case, we don't save it in Google Cloud Storage. It helps us with managing, reducing our Google Cloud Storage requirements. Finally, we do batch processing against Bigtable. So this batch processing, we have several use cases for batch processing, right? One of them is building image index. And for that, we need to scan all available listings, and we use that available listings table that I mentioned that we have. And then for these listings, we retrieve all the image signatures and write them to GCS, Google Cloud Storage, and that partitioned by certain grain by category, and then it gets distributed to a cluster that serves image searches. So we use both Cloud Dataproc and Cloud Dataflow to scan big tables. There is great support for that. So just a few best practices and tricks about Bigtable. So first, pre-join your data. Right? If you have many data sets that share the same key, it's best to put them in the same table, and then you can leverage. Then you can scan and access this data together. Right? You can also leverage atomicity, that transaction support at row level that Bigtable has. And then column families allow you to separate the load with different access patterns. And then with key design, right, first you need to design a key to avoid hot spotting, and we covered that. And there are several methods of doing that. You can use hash of the key. You can choose one of the columns in the data set as a prefix. Or, like we did, you can try reversing your key lexicographically, and that may improve your key distribution. And also, key prefixes help with optimizing queries, right? If you want to, like we do when we want to scan listings for specific markets. And also, you can use key prefixes to represent parent-child relationships. So finally, we use monitoring with Stackdriver, and that helps us with this 500 streams that we need to babysit and manage. It helps us keep track of those. Right? We have custom time series that we've designed, and we post our latencies between when event happened on eBay core side and when the record got inserted to the Bigtable, and also the volumes. And this is a snapshot of one of our Stackdriver dashboards that shows the volume of the data. So you probably cannot see the numbers, but it has all 500 data sets here in one place. And the top one shows the number of batches, and these lines that are kind of on the top, it's about 20,000 every 5 minutes. So it's a lot. So it helps us. We have alerts set of this monitoring. So in case if things are not moving fast enough, we get alerted and we can get in and add nodes to Bigtable or fix things. With that, I pass it back to Misha for some closing notes.
So I'd like to thank very much Leon, and we have the folks from eBay, the team that worked on this, and also we have some folks from the Bigtable team. So thank you very much, everyone, for contributing to this project.